go. Okay, you're hello. Hello, hello, hello. So we got, yeah, from Oliver. This came from Malta. So they're doing some cool stuff. We've been working on a 1P, and I think we're going to talk about 1P ground station, that sort of thing.
From the satellite's point of view.
From the satellite's point of view. So it's a very interesting topic that hopefully will be really useful for you guys. And yeah, without further ado, Oliver.
So, good afternoon all. I am Oliver, and for the next few minutes I will be bugging your brain about a forward error correction scheme and a way to support multiple sessions at the same time while you communicate with the satellite. Now, is there anyone familiar with forward error correction schemes in here, perhaps? No? All right. So basically a forward error correction scheme, for those of you who are not familiar, haven't heard of it before, is a way for you to detect errors while you're transmitting the data and fix those errors in order to improve your link performance. So, as Tom introduced me, I am Oliver, and I'm working with the University of Malta doing my master's work, as I am a master's student, with the Astrea team, where we are designing a 1P PocketQube, and I'm working on the radios and on the satellite itself. So, my presentation will be outlined as follows. I'll first introduce myself, then we'll go over the project systems and the specifications, what we intend to do with the satellite, how the communications module will work, then the data link itself, which we are going to use, a new protocol that we hope to use, and finally the conclusion where we tie up everything together. So, as I said, we are designing a 1P PocketQube, and the goal of this PocketQube is to have an impedance probe where we like to characterize the Earth's ionosphere. So as you probably know, the Earth has the ionosphere, which at very low frequencies, it reflects back the propagation of the waves, but at higher frequencies, the ionosphere basically lets these signals pass through, and we would like to model this more accurately by performing an experiment in space. So the satellite will be orbiting around 500 kilometers above sea level, and we'll have around six passes every day, one at 6 a.m. and one at 6 p.m. With the longest pass being 8 minutes, and we'd like to maximize that 8-minute window as much as possible. Also, at the same time, we'd like to reduce power consumption as much as possible. As you probably know, power on board a PocketQube is very limited. So, the communication systems, starting from the ground station, we are working on a phased array ground station with a digital combiner in order to improve and be able to track multiple satellites at the same time. We'd like to have a forward error correction scheme. As I explained before, you can basically detect errors and fix them. And we are designing everything in-house, all the communication systems designed in-house. So my work is basically in designing both the hardware and the software for the communication system on board the satellite, and I'm integrating a forward error correction scheme into this workflow in order to improve the link performance. Now, the communication system on board the satellite will have this design. So, the scientific payload, it requires access to the antenna in order to perform the experimental tests. We'll have a low power wake up receiver which wakes up the system in order to minimize power consumption, and then a high bandwidth transceiver in order to transmit and receive large sections of data, or relatively large amount of data. And we'll have the beacon which we will use to find the satellite while it is orbiting in space. Now on the controller, we have an integrated microcontroller and an FPGA on a single chip. one from ST, and the FPGA is from Lattice Semiconductors. And we like to use both of them in tandem in order to improve the performance and be more flexible as to the receiver itself. Now, some figures. When performing the link budget analysis, we'd like to have the receiver sensitivity to be able to detect at least minus 106 dBm signal and transmit around 27 dBm of output power from the satellite itself. When you take into consideration the various systems that the satellite will have and the average power that it will generate, the power allocated for a single orbit, the average orbit power for the communication systems is around 75 milliwatts. So we have to be very economical in how we use that power on the communication system itself. The bandwidth and the frequency which we are aiming to use is around 20 to 25 kilohertz for the bandwidth, somewhere between 45 and 48 megahertz, depending on which frequency we are allocating. So, how will the communication system work itself? The system will have around 5 modes or 5 states, which will be switch between those according to the instruction or which we configure. So mode 0 is the basic, where we will be in listening mode, where the satellite will listen to the channel, whatever it is receiving, and perform action should it receive a particular instruction. Then we have 2 basic telemetry transmission modes. The first is the basic telemetry mode, where we transmit simple parameters for the satellite very frequently, maybe perhaps around 5 minutes at each time. And the detailed telemetry mode is where we transmit more detailed parameters of the system. For instance, the basic telemetry mode, we can transmit the voltage of the unregulated battery voltage. And in the detailed telemetry, we can transmit a history of the an orbital history or half of, or some of that history of the unregulated battery voltage. So we can know if an error exists in the battery voltage, we can fix it and prevent it. The logging mode is when we want to instruct the satellite to change the particular logging behavior, so we can again know more details about the system itself. For instance, maybe perhaps the maximum power point tracking of the electric power system is not being optimized correctly, so we'd like to, before applying a firmware update to the EPS system, we would need to further test in order to prove and validate our hypothesis. Now, something which I will be focusing on is the critical maintenance mode, where we would like to transmit perhaps firmware updates to the system. And so it needs to be a very high integrity link. The first 4 modes only require a simple and basic communication link. In fact, we plan on using based on the AX25 protocol. However, the last mode, the mode 4, requires a bit of a high integrity communication link. So we need to optimize as much as possible the communication link in order to fix any errors as much as possible. So mode 4, we'll be able to alter the behavior of the individual controllers more directly. It can even be used to send firmware updates and perform maneuvers. For instance, if you have a thruster-based system on the satellite, you can change how it behaves by sending instructions, depending on the instruction set we set. And it can also be used to get specific controller feedback. However, we will be using it for sending firmware updates to the system. I think it should be able to support communicating directly to the individual controllers on the satellite, and perhaps even bypass the onboard computer, because for some reason or another the onboard computer may be experiencing some errors or some radiation faults, and so we would like to bypass it completely and instruct the particular satellite more directly, the particular controller more directly. Also, this protocol should be allowed to create an easier queuing system of instructions from the ground station point of view, and most important, it is used to utilize the time window, that 8-minute time window, as much as possible, and in the most efficient way. Remember, we only have around 8 minutes to find the satellite, synchronize with it, and transmit our information and get feedback from the transmission itself. And so, in order to do this, we opted to use a forward error correction scheme. Now, why? Basically, the forward error correction scheme reduces retransmissions. This will ultimately increase the link efficiency and improve the link reliability, and it will allow the receiver to operate at a lower signal-to-noise ratio or at a better bit error performance. However, this comes at a cost, as there's always a trade-off in engineering. This increases the processing power and thus the power consumption, and encoding and decoding times are longer because now you have more complicated tasks to do, as the forward error correction scheme is mostly an iterative process. And in order to be a valid correction scheme, you will have to introduce redundant bits in order to be able to detect and correct the errors. So this increases the overhead. Now let us take a look at what existing data link protocols already exist for amateur satellites. There are basically two, which are the FX25 and the AX25. Now the AX25 doesn't have a forward error correction scheme, whereas the FX25 has. And the AX25 is is used more than the FX25. Neither of which allow us to communicate with more than one controller at the same time without adding additional layers internally to the payload. So it have basically a more similar application to the OSI model. Now the two of them perform packet synchronization a bit differently. The X25, basically you search within the incoming bit stream of the FX25 in order to find a 0, 6 consecutive ones, and then another 0. Whereas the FX25 utilizes the correlation tag, which also describes what error correction is being used in the packet itself. The benefit of the FX25 is that it is backwards compatible to the X25. So if you have an FX25 transmitter and an AX25 receiver, the AX25 is embedded within the FX25, so the receiver is still able to receive the data. However, it will not be protected by the forward error correction block present in the FX25. Both of which add a significant amount of overhead, as you have a bit stuffing process in which you basically search throughout all the bits, and should there be 6 consecutive ones after each other, you place an existing 0 in order to not to have the start and end flags in the packet itself. Now the FX25 does this as well and adds redundant bits at the end. The encoding time also varies between the two protocols, as the AX25 is very easier to decode, whereas the FX25 takes longer due to the iterative process I mentioned before. However, the bit error rate is significantly improved by the FX25 than the AX25. Nevertheless, these two protocols weren't sufficient for application, so we sort of developed our own protocol, and we named it, name it the MT25 for legacy purposes. Now, all the protocols, the AX and the FX, allow multiple frames or multiple packets to be transmitted during the same transmission. And so the MT25 should be able to perform that as well. So basically, you first transmit the preamble, which allows the receiver to synchronize with the incoming data stream by having, in our case, 6 bytes of OXAA, which basically translates to toggling bits in the bit stream itself. But not all receivers take the same amount of time in order to synchronize and obtain the correct data rate. So, for instance, in some cases, you might be able to synchronize within the first couple of bytes, and in other cases, you may be able to synchronize within the first few bits. So in order to explicitly know when the first packet is going to arrive, we added the synchronization word, OXD4 and OX2B, which are mirrors of each other. When you see the bitstream format itself, you realize that these are mirrors of one another. And this way, you will know exactly when you are expecting the start of the frame. And to further protect it, each frame is then, or each packet is then delimited by the correlation tag, which is 8 bytes, 8 bytes long, and are chosen specifically so that when you are shifting the data to a sort of like a shift register, with each shift you are performing an XOR function. And so the correlation, when you perform this XOR function, as it is drops significantly low if there is no correlation. So keep in mind that here we are expecting errors to occur. So if you have, for instance, let's say that the correlation tag is AB. So you have 10, 10, 10, 11. And as you are shifting it, you are first seeing, so you start with an empty shift register. So you have 7 bits 0, and the first bit is the one which you are trying to receive. That means that when you XOR that function, you have a low correlation, because the output would be, if I'm not mistaken, would be, I think, 1 itself. And so the process keeps going, and so the next iteration would be 5 zeros, 1 and the 0, and so on and so forth. Now at some point, you get a higher correlation number because all the bits are aligned. And at this point, you know, okay, that I am synchronized. However, if you have an error in between those codes, if one bit is flipped, you would still get a high correlation tag, a high correlation number, but wouldn't be the maximum. And depending on this level, you are allowed to synchronize much more efficiently with the data and be able to synchronize even with errors involved. Now, then we have the packet header itself, which will go into more detail. The next slide, 256 bytes of usable data, which is the same for the X25 and the X25. A 16-bit CRC code to further protect the packet itself. Keep in mind that the forward error correction is not foolproof. You may still have some errors which are passed through. Whereas the 16-bit the CRC code is much simpler to, it's much easier to detect errors with the CRC itself. And we would like to use a fixed length packet, as this will simplify transmission, and so we added the padding. And finally, we have the code block itself, the parity bits which we will detect and resolve the errors. Now, moving on to the header, when you compare to the X25, you have around 6 bytes of the call sign address, and that gives you that means that you have 12 bytes just to address the satellite. Given that there aren't a lot of satellites out there, I think we saw that this would be is a bit quite large, and so we opted to use a numerical value of 2 bytes long. This would give you around over 65,000 individual satellites and ground stations, which is quite more usable. And then you have the payload and session ID in 1 byte. So the payload is an address in order to determine the type of data and who will use it. So let's say that you want to transmit a firmware update. Now the onboard computer will probably program the new device that you are sending, the device which you are instructing. So there, for instance, the payload ID, payload destination would be, for instance, 0, as this is intended for a firmware update. However, let's say that the onboard computer has experienced some errors, and for the time being is being reset and trying to catch up to the previous process. So you can basically address each individual controller on the satellite itself. So if you have 3 EPC modules, you can address each individual one and send instructions to that particular controller. Also, when used in conjunction with the session ID, you can start the transmission of the firmware update, and in between you can initiate another session by changing the session ID, and the comms module will realize that this is a new session and that the payload in particular is intended for a different controller. So basically you are, without stopping the firmware update itself or cancelling it or having to start again or adding additional complexities in the system, you are allowed to transmit a different instruction sort of while you are transmitting the rest of the instruction. I don't know if this was clear. But that's basically what it allows you to do. Then the last 5 bits are the packet number, total number of packets, and the length of each packet. Now these 3 parameters together will allow you to detect the start and to detect any missing packets due to synchronization issues in the first or last data streams, the first or last packets that you are receiving, as the numbers will not be coherent with what you are expecting. For instance, if the first packet is 2, the first number is 2, then you know that you missed the first one. Whereas if the last packet received was 48 out of 49 out of 50, that you know that you missed the last packet, and so you can easily request that packet particular. The packet length is important especially for the last packet, as you are assuming that in between you are maximizing the maximum payload itself. So you want to transmit on 0 to 4 bytes, or let's say you want to transmit 1,000 bytes. You'd have the first 3 packets filled with 256 bytes, and the last one filled with 256 minus 24 bytes. But how can we know for sure that the MT25 is better than the X25 or the FX25? Well, when you look into take into consideration all the bits and why they are there, and keep in mind that we would like to have the session ID, payload ID, and at least the number of packets that you are expecting. In the AX and the FX25, you are reducing the maximum payload from 256 to 251 bytes. Now, when you work out all the math, which I did, the information in each packet, basically the user data here, the 76%, 58%, and 66% express how much payload data you are transmitting with each packet. So in the first one, with the AX25, we have 76% of payload information, which means that the 24% are overhead. In the second case, we have 58%, which means the 42% are overhead. In the last case, we have 44% overhead. Now, when you check, well, this was bigger before. This is basically the bit error rate on the y-axis, and is the signal to noise ratio on the x-axis. And the red is the case when you are not using forward error correction, and the blue is the case when you are using forward error correction scheme. I don't think I can zoom in right now, but for a given bit error rate of 10 to the minus 4, which means that you are expecting one bit error for every 10,000 bits that you are expected to receive. The MT25 and the FX25, as they are forward error correction protocols, you need a margin of around 5 dB, a 5 dB margin. For us to obtain the same performance with the AX25 without forward error correction, you need an 8 dB margin. Now this means that basically you are with the use of a forward error correction, you obtained at least 3 dB gain. However, when you're comparing the MT25 and the X25, as they are, as they were the first and second, the most, the best user data, has the best user data performance than the FX25. The 3dB gain comes at a loss, at a cost, of requiring to transmit around 8% more user data. Now, should this be allowable for you, you can use the MT25 or a similar function to obtain a better performance. Now, however, in most cases, you have a fixed margin, unless you plan on changing remotely or physically the satellite hardware, which is a bit impossible. You have a fixed margin, a fixed signal-to-noise ratio on board the satellite. Now, by using the forward error correction scheme, you are improving the bit error rate when you want to transmit very particular and important payloads. As I wish this was larger. Basically, if you let me continue. So, let's say that this at this point here, this is around 6 dB. So, at 6 dB, we have around 10 to the minus 3 bit errors, 10 to the minus 3 bit error rate, and here we have 10 to the minus 5. So now you decrease the likelihood of a bit error rate by a factor of 100, which is quite significant. Okay, so this brings us to the end of the presentation. Now, here we combined two existing protocols, the AX and the FX25, in order to create a new and improved protocol. This will use the link much more efficiently, and as you are not retransmitting packets but are fixing the packets, which will ultimately reduce the power consumption, as each time if you have a particular packet which had an error, the satellite will transmit to the ground station requiring more power in order to instruct the ground station, hey, I had this packet wrong, can you please send it again? This is removed. At the same time, we are improving the bit error rate. Yeah. And I think this will basically provide a new challenge and a new opportunity for the radio amateur community in order to communicate with new protocols. So, thank you for your attention. Are there any questions? Okay.
Questions for Oliver? Questions, Joe? Yep.
How far along are you in the process of testing this in the lab and actually?
Yes, basically I've tested it on my PC and on the microcontroller I intend to use with, I don't know if you saw two values, 1037 and 813. Those are basically the size of the words I am testing with. It's quite close to be, I just have to integrate the MT25 itself, but the forward correction scheme is working perfectly on board the microcontroller. I intend to also port some of it on the FPGA, which will ultimately improve performance significantly.
Okay, thank you very much, Oliver. Round of applause.
Thank you.
So we've got another talk coming up now from America, so Sean Casey. I've been Sean for a few years now. I'm in Silicon Valley. I think this only before people met actually started out well. I went to Silicon Valley. The first week I started the company. Then I sit in my house in PSAC and started a company called PocketQube. So I bumped into Sean back then. He's now working at Atlas Space Ops. Yep. And do some really cool stuff with the base station networks. So if you guys are thinking about your ops plan, obviously thinking about how many access can I get, you have to have a lot of base stations, and that's where sort of Sean's business comes in. And yeah.
Great.
Hey, thank you very much. Thank you, Tom, for that introduction. It's a great pleasure to be here. It took a bit of travel to get here from California, from the sunny Bay Area, but I was glad to get here in Glasgow. So that I appreciate the last bits of summer here in Scotland today. Oh, great. So we've got our slide deck up. And I know Tom from the last couple of years. I ran into Tom this summer up at Utah, and was glad to see that his PocketQube program is still going strong. Tom is one of many people that are entrepreneurs in this space, and one of my jobs in the Bay Area is to serve as a mentor for the Founders Institute, which is an early stage incubator for startups, a wide variety of startups across a whole number of verticals. It also includes space. One of the slides that I include in my discussion about early stage companies is this from, with Russell Crowe and A Beautiful Mind, because I think there's not really much difference between being an entrepreneur and just being crazy. When you look at the future and you have a vision, you're not quite too sure whether that vision is grounded in reality or not. And I've known a number of entrepreneurs who spend a lot of time talking to everybody, saying, is this a good idea, blah, blah, blah. And they don't really focus on execution. The great thing about Tom is that Tom, for the last couple of years, has been focused on execution, and execution in two areas. One is retiring technology risk, and the other is retiring market risk. The technology risk, of course, is, will PocketQubes function, does the radio function, does all the computing function? The market risk is who's actually going to buy this product. And I don't know how many other people in the audience are thinking about taking their PocketQube concept and developing it into a company. Is there any interest in that? I know Tom's going to raise his hand. But yes, no, you guys are mostly focused on academic applications. Is that so? Yes. Well, the PocketQube is a great technology demonstrator, but when you ask about the cost for PocketQubes, your biggest cost is probably the opportunity cost. What am I not doing while I'm working on this? So for our young students, I think our young students are thinking, well, gee, where is the opportunity in working on PocketQubes? And there's tremendous experience that can be gained by building and flying your own hardware, but we live in an economy where this hardware is a disruptive technology for existing solutions, existing communication solutions. We heard talk about Earth observations, there are talks about IoT. You should be thinking about how this technology can provide capabilities for a market that's not currently using that technology. So, what I may be saying is crazy, but you should really think about it. And you think about it in terms of demonstrating, you got it? Yeah.
Keep scrolling down with us.
Yeah, I got it. Right. So, that being said, oh, I see, it just scrolls down. All right, very good. We just started the last talk talking about ground station contacts, and within the new space sector, there are lots of constellations that are flying. You can build your own ground stations, and that certainly works well. If we wanted to put a ground station here on the roof of this building, and we had our satellite in a sun-synchronous orbit, we'd probably get somewhere between 5 to 8 passes per day, maybe, and that those would be at different elevation angles. So in a LEO orbit, the most you're probably going to get on a particular pass is about 8 minutes. You're going to have to carve out a certain amount of time for acquiring the target, then establishing the link, and then breaking the link, finishing the handshake, and getting done with that. So out of your 8 minutes, that's probably about 2 minutes of overhead, which leaves about 6 minutes of communication time. That's when the satellite's going directly overhead. If it's going down at a low elevation angle, that time of connection is going to drop down. So you're probably going to look at, let's say, 5 to 5 to 8 passes, with the pass time is anywhere between 2.5 minutes, because that's about as low as the horizon as you can get, all the way up to 8 minutes. The mean of that distribution is probably anywhere between 2.5 to 6 minutes, and then there's a peak up at the top. Is that enough time to do what you want to do? That would be the question for people. I mean, how many passes do you want to get with your satellite? The industry is moving towards 24/7. In my pocket, I've got a cell phone. You know, when I fly out here from California to Glasgow, I'm really kind of irritated if my cell phone doesn't have connectivity. And so one of the things that's coming online today is 24/7 connectivity for constellations in LEO, in low Earth orbit. And this is what Atlas Space Operations is providing. My question for the community is, was PocketQube interested in a broader base of communications? Because I know it's certainly of academic interest to build your satellite, launch it, build your ground station, do you know, a modicum of communications with that satellite. But would you like to have greater bandwidth, greater connectivity? So Atlas is in the mode of building ground stations, developing a network, making sure that network is integrated, and then providing that to whether it's academic customers, industry customers, or government customers. We're based in the U.S., so we have a number of U.S. customers. And with that, it's an application that we call Freedom, which provides uniform connectivity among all the various ground stations we have. It interfaces with the, well, this is an informative slide. The best laid schemes of mice and men gone after glide and leave us lot not but grief and pain for promised joy. That's the, I don't know how many people are a fan of Robbie Burns, but if you're not, To a Mouse is the one poem that you should know as an engineer, because that is pretty much what sums up the engineering experience. Here, we have a number of products that are clearly shown on this slide, where it includes both the Freedom software that we have, the Freedom Network, which is our network of ground stations, and then a phased array technology that we use for tracking multiple satellites in LEO, and then technology associated with launch service providers. You might say, oh, look, you know, we're up here in the UK, up in Scotland, but we have a number of sites that are distributed on a global scale that gives us about a 30-minute to 45-minute latency for satellites in LEO for a variety of orbital inclinations. That's sun synchronous, that's inclined orbits, that's also equatorial. The networks we have are supporting UHF, S-band, X-band. We're looking at Ka and Ku band. But all of these sites are interfaced to Amazon Web Services. And you know, for your kind of applications, which is a low data rate, it probably doesn't matter, but if you're focused on Earth observations, that may be important. But all of our software is written on top of the Amazon Web Services cloud infrastructure, so that all you have to do is just tunnel to Amazon, tunnel to Atlas to a secure VPN, and then that allows you to connect up with all of the ground stations that are in our network. Aspects of the Freedom software, like with many things, timing is important, and you've got to figure out when your satellite is going to be overhead. We have a partnership with those responsible for tracking satellites, and the nice thing about PocketQubes is that they are trackable. So within the Freedom software, you can put in your 2-line element orbital parameter, and and then the network will figure out when it is the right time to schedule a pass with the right ground station to get your data down. So all of this is being done in software, fairly straightforward. I mean, climbing the learning curve on any software is always a challenge. But we've tried to make it as easy as possible such that you can schedule your passes within any element of our network. It's uniform so that you don't have to worry about whether the pass is going to be in Ghana or up here at the Isle of Man or in the US. We also take care of licensing requirements for transmit for international territories. And then we can provide assistance for you getting your own license for your satellite. As I've mentioned, an aspect of freedom is the integration among differing ground stations. And I don't know how people are thinking about their own ground stations. They're probably just UHF antennas that are plugged into the roof, but we have a number of different technology providers, different service providers for their ground stations. And rather than having to deal with the differences among ground stations, the Freedom software provides a uniform look and feel among the ground stations in our network. So you don't have to worry about if one antenna is from Orbcomm and another antenna is from Comtech or whoever. That the software provides all of the interfaces, so it has a uniform language for commanding of antennas, and then provides a uniform data stream on data metrics associated with the antennas. So you can see the quality of the link, how long the link lasted, and when the next link is expected. Everybody loves pictures of hardware. So fortunately, these showed up and they weren't deleted, like out of the last slide. But these show some of the ground stations that we put up in the last year. In the last 12 months, we've built 13 ground stations. And by the end of 2020, we should have another 17 ground stations online. That network will provide a low latency contact for anything that's in a LEO orbit. That means pretty much every, let's say 30 minutes, 20 to 30 minutes, you can be able to get your data down. And the question will be, is that important? Do I care about getting my data today or tomorrow? What does that look like? Do I care about tracking my satellite on a daily basis, you know, every hour on the hour? Or am I happy just with my one ground station and getting a few passes every day? But these are stations that we built, and I would say if there are any young students that are interested in a career in satellite communications, feel free to come talk to me, because we're in the process of expanding our ranks and hiring, and we work on a global basis. So if you like to travel and you like to spend time in Tahiti or Guam or Japan, come talk to me. Happy to chat. We also have a number of other ground stations that are listed here. We basically do a portfolio of land bank sites. Land bank sites are regions around the globe where you can actually build and operate a ground station. So those land bank sites are then typically pre-qualified, where we have an agreement with the landowner about power and internet access. We make sure that you're actually able to build antennas on those locations and that they're radio quiet zones. We heard before whether there are restrictions in different parts of the globe about the RF broadcasts and RF reception. We can pretty much handle all that with the land bank sites that we've got that also are on a global scale. We've got several hundred. And so if there's a particular location where you'd like to put an antenna, we'd be happy to support you on that. One of our antennas, of course, is down in sunny Mojave. I don't know if anyone's been down to Mojave at all, the Mojave Spaceport, very exciting place. You've got Virgin Galactic down there, you had X-Core, you had Straddle Launch. So we also use the spot as a center for RF communications. This is one of our S-band dishes with a number of parameters on it. All of our sites are cataloged in this fashion, where you can see what we have as a UHF antenna, what we have as an S-band antenna, what are the properties of those antennas in terms of their receiver noise and sensitivity, and then their broadcast power. One of the services that we offer is for identification of lost satellites if you have an emergency situation where you're not quite too sure where your satellite is. We can help you in identifying the location of your satellite and being able to track it. We're actually building out that service, and if you have a satellite which is tumbling and needs an extra big signal in order to get through to it, we can accommodate you on that. In the fiber optic business, they typically say that there's a bunch of dark fiber out there. I would say the same thing is true in the satellite communication sector. There are a number of antennas that are available that are perhaps undersubscribed, and we have partners where we can facilitate the use of those antennas. So, you know, if you're thinking about, gee, I want to go build a site, one of the first things you probably want to ask is there a site that's already out there which is suitable for my needs? So within Atlas, we have a number of partners. This is one of the sites that's up in Brewster, Brewster, Washington. This is one of the old ICO antennas, and this is actually probably a big hammer to hit a PocketQube. But it's a 7.6 meter dish. It's one of 5 dishes that are located in Brewster, and the Brewster site is one of 10 sites on a global scale that are old ICO intercircular orbit antenna farms, and that these are also available if you're so inclined or if you so require. As I mentioned, we've got a lot of happy campers for ground stations that we built around the globe. And these are some of them in Ghana. We also have a UHF antenna that we built down in New Zealand that supports Rocket Lab. Typically, we look at all phases of the satellite program for LEOPS, launch, and early operations phase. What does the satellite need as it's initially brought to orbit and commissioned? Then we go into the early operations phase for establishing communications with the satellite and working on the satellite checkout, and then into normal operations. So I think one of the things that's important for PocketQube is not how everybody functions individually on their own, but what kind of functionality can you provide as a group, as a constellation, because that's where you're going to get the economies of scale. It's not, gee, I've got one satellite, but how am I part of a constellation of PocketQube satellites that then adhere to certain standards so that you don't have the non-recurring engineering costs associated with a unique mission. And when I look at the PocketQube community, I'm like, okay, well, what are the things that you can do that are the same, and what are the things that you need to do that are different? My bet is that communications, unless, of course, like the last talk where we're like, hey, you know, let's implement some new forward error correcting schemes. Let's push the envelope on technology. But what you'd like to have is you'd like to have standards that we talked about this morning, not only physical standards, but communication standards, such that it reduces the costs of an individual operations for an individual PocketQube. And for much of the discussion of the last 2 days, the emphasis has been about lower cost. But what I think the real important message of PocketQubes is not lower cost, but greater functionality at the same cost. that you can fly a major constellation of 10 to 20 PocketQube satellites as you could with a smaller constellation of CubeSats. So there's a lot of constellation and swarm technology that you can demonstrate with PocketQubes that you couldn't demonstrate at the same price point for CubeSats. So I think this is a very exciting point in the industry. Yes, we've been flying CubeSats for the last 10 years. Yes, we sat at a meeting 10 years ago where everyone's like, gee, aren't CubeSats toys for academics? I do not believe that's the case for PocketQubes. PocketQubes are a disruptive technology for LEO and can demonstrate swarm and constellation communications, docking, distributed networking, and that these are the things that this group and other groups should be thinking about, and I know they are thinking about it. One of the aspects that I think is important about Atlas is that we're able to accommodate new technologies. If you look at our standard ground station configuration, it's got an antenna, it's got a modem, it's got a bunch of cables, but what we can do is if you have a particular radio that you want to fly on your PocketQube, we can accommodate that within our ground station. If there's a technology that you need to take and scale for the PocketQube constellation, we can deploy that on our ground stations. And this shows, just plugging in a piece of hardware into a rack that's associated with an antenna, and then being able to connect that to the Freedom software, and so that it's all integrated and it functions uniformly. If that technology is a software-defined radio, even better, where you can deploy the hardware and then reprogram it with a forward error correction code, with whatever other coding you want for the radio communications. And then all of that could just be uploaded into the Freedom software and then into the box on the network. So we try and maintain a fair amount of flexibility to support innovative ideas within the environment. And if you have such ideas, please let me know. Again, you can see here's some of our racks. It's a standard 19-inch rack. Just plug it in. And the purpose of this is, hey, there's a fair amount of empty space on those racks. We make sure all this stuff is air conditioned and cooled. And again, if you want to climb the learning curve and do all that yourself, it's a good academic environment. But on our end, we have the economies of scale because we're not just dealing with PocketQubes. We're not just dealing with CubeSats. We're dealing with some of the biggest constellation customers that are out there. And you probably know who some of them are. I was off visiting with some of these guys earlier this morning that are here in town in Glasgow. Pretty pictures of some of our engineering team. This is, in the front is Mike Carey, who's our chief strategist, but in the back, we have a lot of young engineers that are actively going around and building our networks, debugging them, supporting them. So if you're interested in joining Atlas as an engineer or scientist, we'd be happy to have a discussion with you. If you're interested in broadening your ground station communications solution, we'd be happy to talk about that too. You can kind of figure out what the pricing point is for many of these things, but I can tell you it's an extremely competitive environment, and I really do think that PocketQube should be designed with a communication scheme in mind such that you can leverage the infrastructure that's being built, not to support PocketQube, but for CubeSats and other large constellations. Today, we've got satellite companies that are thinking about building 20, 50, 100, 200, 400 satellite constellations. This is what's going to drive the ecosystem. Atlas is part of that ecosystem, and I think we can use some of our ground station infrastructure to help provide greater connectivity for the PocketQube community. So with that, I close it for questions, and I'll be around for the rest of the day if you'd like to talk further. Yes, sir.
When you mentioned that this rate was off the PocketQube developer, what would I be looking at as a real ballpark? Being able to pull my data down, say I want to bring data down twice a day, half a meg a day. Do you have a pricing structure or is it a contract?
It's, you know, I'd say pricing is pretty much on a per minute basis. And what you could say is that, normally for Constellation, it's like, a couple of dollars per minute. So if you look at your route station, if you look at your pass, that's probably about 8 minutes. So it could be from like $8 to $16 pass. And it depends on, it depends on what you're looking for, what the use case is. Because, you can always build your own Yankee ground station and operate it from your roof and just pick up the data, as things go overhead. But if you're looking for greater connectivity and you're looking for a global footprint, you've got to do something other than just have something on the top of the roof. So I always look at it and say there are 40 minutes in a day. You can take whatever the cost is for your ground station and kind of divide it out. Say, hey, I want to make some money off of it over 3 years. But we typically do. I like to focus on permanent pricing, and that's permanent for just the data transfer. Where we carve out the overhead, the acquisition, something like that. Yes, sir. Marty? By coverage, you mean terrestrial coverage or frequency? Yeah, like I said, for UHF band, if you look at an orbit and you say over a 24-hour period, we should be able to get the data down in less than 45 minutes for most cases. So for most orbits during the day. So 500 kilometers, your orbit's like 90 minutes. And so that's basically picking up every half orbit throughout the day. And it's probably at like the 85, today it's at the 85% level. As we build out our ground station network, by the time we get to 2020, it should be less than 30 minutes.
Thank you very much, Sean. Give a big round of applause for Sean. Cool. So we've got another talk, we're going to have a break I think after this. So I'd like to introduce you to Simon Pawlicek, direct. So Simon's just joined Edinburgh Uni. We've been working with him for a number of years now. Previous role at Harry Watt on scene, and Simon just worked together back in the day doing antennas and some that was reduced. And Simon's been working on some really cool stuff with applications in the monkey worlds. How do you make your antennas really good and really small? That's a really hard question. It's something that Simon's been thinking quite a lot about, building quite a lot of cool hardware and cool simulations. So, yeah, I'll give it to you.
Thanks very much, Tom, for that introduction. It's really nice to come to this talk and see Costas, for example, here. He was my first postdoc. He's actually, the antennas that he designed with Tom about 4 years ago are on the second the satellite there. So it's really nice to see. So we'll sort of go through an evolution, that I like to call it, about the RF antennas that I've been working with colleagues and myself and other PhD students at Harry Watt in Canada as well, in Canada originally, and at the University of Edinburgh now. So hopefully you learned a little bit today. I'm an RF antenna engineer, microwave engineer, so if you don't ask or understand something, ask a question afterwards, please. Okay? So actually, it was actually really nice to see a lot of the people today talking about the challenges that you see with deployable antennas. I mean, this is the whole motivation for this research idea, this problem, this challenge, because typically, you have extendable antennas on something that's on a PocketQube antenna or a platform that's 5 centimeters by 5 centimeters, and you want that to work at UHF. So if you look at the wavelength, you're almost at a meter in terms of that wavelength. So to design an antenna that fits, that is not deployable on that size, on that platform, that's 5 centimeters or even 10 centimeters on a typical CubeSat, is actually really, really hard and really challenging. Okay? So as we know, there's lots of applications for these types of CubeSats, as you know much more better than me. Again, I'm an academic doing this research on the antenna design and trying to avoid these typical deployable antenna systems and provide an alternative. Okay, so I should start really where this work sort of started out. So I was actually very lucky enough a couple years ago to work for the Canadian Space Agency and helping them to design this, basically this CubeSat here. So this was flown in space, was launched a couple years ago. I think the mission ended actually earlier this year. But my contribution to the work was actually designing this antenna here, this folded shorted patch. So this was a UHF antenna that worked at around 400 megahertz, 407 or 405 exactly. And it basically was an array of patches, and they were folded and shorted to actually make them extremely compact and fairly small. So if you look here, the size is 0.2 lambda by 0.2 lambda. The typical, regular patch that you make is 0.5 lambda. So this antenna here, this actually got us a number of awards recently, and here you can actually see more of the structure. So it's actually a multi-layer piece of metal. So in this type of larger CubeSat application, we had the luxury of having a bit of weight, I would say, lenience. So we could actually make the antenna a bit more heavy. So it was actually made out of aluminum. But there's no harm in adapting that procedure to other antenna designs and more novel, lightweight, metallic-based, dielectric manufactured materials. Okay, so to actually make it circular polarization, you need a feed system on the bottom, which generates circular polarization. So this is in academic papers already published now. So an outline of my talk is going to be looking at the basic of this 400 megahertz type of folded shorted patch antenna design. So hopefully you learned something. I'm not going to go through a lot of equations, nothing like that, but just basic, input impedance. How do we design an antenna like this? So hopefully you gain some knowledge. And then extending that to a 1.1 gigahertz design, so even making it effectively a little bit smaller, but for other implementations. So for a pico satellite. So with talking with Tom and Costas for the last couple of years, they said this design was really great, really cool, but we needed to work on a pico satellite, not a CubeSat, but then to have it to work at 1.1 gigahertz. So you could actually connect to other satellites, other LEO satellites at the L band, so at around 1.1 gigahertz or so, for connectivity to the existing multiple satellites. So this here is the original mission, the M3XM satellite mission. You can see that the antenna is actually right there, and there's an implementation of it. So I'm very happy to see that this got some traction in space and worked. So when it worked, you feel pretty good when everything works. So again, what we're actually doing is we're taking a basic patch antenna. Okay, this is a PIFA antenna where you have a probe, and effectively you short it at the center, so you get a lambda by 4 type of antenna. And then what you do is you fold the ground plane over. Okay, so that's step one, and you keep folding it. Okay, and you keep folding it over, and there you have a very compact patch. It's nothing more complicated than that. Okay, so if you have one of these elements, you can easily get linear polarization. Now the challenge or the benefit with this is it becomes more compact, obviously, but from an electromagnetics point of view, there's some challenges that come with this. You lose bandwidth, right? That's the typical thing. So if you lose bandwidth, that may be for some applications, for example, for telemetry, or you may be okay with a reasonable amount of low bandwidth. Okay, so with this, you can actually take a basic transmission line model and on a piece of paper, calculate what your input impedance would be to this antenna, what frequency it would need to work with, by actually just using basic transmission line parameters. And you can make this in PCB, which we've done. You can make this with basic metal sheets, as we've done here, and the modeling is actually quite straightforward. So these are maybe the most complicated equations we'll probably see in this seminar this week or today, but it's really not too hard to apply these equations. Just look at the input impedance and find what the antenna would be matched at based on a certain length. So you can take simple equations like this and say, okay, my antenna needs to be matched 407 megahertz. Well, I can find the effective lengths of my antenna elements, the meandering and so forth, and then I actually also get it to work at different frequencies and so forth. So how does this actually work from another physical point of view? Well, I actually see in a typical patch, you have 2 radiating slots. You effectively have one, at the edge, which is at the top reading on the pin. So it's basically transmission line theory applied to this type of antenna system. Okay. Now, again, to get circular polarization, you need 4 elements sequentially rotated. So there's a rotation of 90 degrees. So if you get 4 of those elements, then with a feeding circuit, you can actually get circular polarization. Left hand, right hand, depending on how you prefer. The other benefit of using multiple elements is that your gain improves, right? So it's an array. Now, there's no harm in that. You could do this type of antenna system with a phased array approach where you do sort of beamforming or that sort of thing. Again, this is just a simple passive structure that allows you to, say, do telemetry positioning or communications with other satellites. Okay, so the feed system that is there that is required to do this is on the back side of the antenna. So there's actually probes, jumpers from microstrip to those probes to actually allow you to connect there. Okay, so if we look at the stack up again, you have the 4 elements on top, and a ground plane, and then an antenna feeding circuit, and we'll go into that in a little bit more detail. So if you thought that the challenging work was in the antenna itself, well, it's not the only challenge, right? Because this all has to be integrated in a certain platform. So you actually have very compact feed circuits, okay? Hybrid couplers, 90-degree couplers, 180-degree couplers as well, to enable that sequential phase rotation for circular polarization. Okay? So if I look at that's really too bad because on my screen I see this, but I don't see it here. Maybe if I go back, you can see on this picture here, those are actually in the middle 180-degree hybrid coupler, and on the left and the right there's actually 90-degree couplers. So this feed circuit as well is extremely compact, on the order of 0.2 lambda by 0.2 lambda or less. Okay, so this is just an illustration that if you look at a regular coupler, it's on the size of 0.5 lambda. So you're fitting 3 couplers into a space where you couldn't even fit one if you use conventional microstrip engineering design, passive coupler design. Okay, so again, I'm not sure why it's not showing up here. Apologies for that. So we can maybe skip that. So again, here, just to reiterate, you see the 180-degree coupler to 90 degrees, and this was a test circuit that allowed us to actually measure the feed system before actually putting the whole thing together. Okay, so if we measure the feed circuit, you can see you have decent matching at 400 megahertz, equal amplitude and phase, equal amplitude excitation of all the elements, and then sequential 90, minus 180, minus 270 at 400 degrees. So it's actually quite interesting because this circuit was designed to be very wide band, but the antenna is very narrow band. So this feed circuit could be used for many other types of antennas if they were redesigned for that specific frequency. Okay, so here's some measurements of the antenna structure. So you get very good, cross polarization level, decently low, below 10 dB or better. So this was designed for right-hand CP in this application here. So you can see over a bandwidth, it's pretty decent. Okay, so if I go here to the next page, what we can see is that this is the entire encapsulated antenna system. You can see roughly at 400 megahertz, the VSWR, the matching is fairly good, almost pretty well matched. Now with a metallic-based structure like this, we had to come up with here's also showing you the Borsite gain, the realized gain versus frequency, and the axial ratio. So the axial ratio tells you how circular polarized the antenna is. If it's 3 dB or below, that's a decent CP antenna. I've seen Costas design CP antennas that actually have higher CP gain than that, but he still thinks that's okay. So 3 dB or below for the axial ratio is what you really want to have. So this antenna decently has a decent axial ratio, meaning that it's a nice pure circular polarized antenna. If we look at the left curve, it shows us the simulated gain. So what these two values here are, the dots are simulated in this illustration and the lines are measurements. So one thing we actually had to do with this antenna is because there were so many dimensions, so many tolerancing issues that were introduced, we actually had to come up with a way to tune this antenna. Okay, so this was sort of an interesting design effort that you'll never really get out of looking at this paper, but if you think about how you make this antenna, well, if a machinist makes it, there's going to be huge tolerancings that they may be able to accommodate, and that would drastically affect the antenna performance. So one thing we had to figure out is, before we actually made this, is how can we actually tune it to the correct frequency. So what we actually were able to do was just basically use transmission line concepts, microstrip theory, and say, okay, well, let's make our top edges a little longer. Okay, if we make them a little longer, then we know that we'll overshoot the frequency, but if we edge them back, remeasure, etch them back, remeasure, etch them back, remeasure, then we can see that we can actually get back to the original frequency that we want. So on all the edges, you can see that we actually recess the values by a certain amount. So originally, the total vein length, the length at the top, was 55 millimeters. And then after optimization and simulations, we got it to be 52.5. And when we actually measured it, we got it to be 53. So from an engineering point of view, to get things within half a millimeter for the measured structure is actually quite really nice to see. So, there's a lot of students in the room. So when you design an antenna, you design a circuit, you design something, you need to introduce some sort of safety features, fallback. How do you accommodate for things not working? And I see a lot of people talking about that, but it also applies to the circuits, right? The coding schemes, as well as the antennas. So you sort of have to think about, you can only make this thing once, if you're lucky sometimes, so you need to say, okay, well, we can make it once, knowing that it won't work. How do we make it work after post-fabrication and production? Okay, so where did that research go? So then we thought, well, how do we make this into a low-cost type of structure? We took that and made a perfectly PCB type of antenna, so something that's multi-layer printed, and that worked at 400 megahertz. Next idea, which actually Costas introduced, is using and integrating these types of patches on solar panels. So I'll go to that a little bit more. But what was sort of interesting after coming from North America and speaking with Tom when I first came here is that he said, okay, well, I'm working on a pico satellite, right? Something that fits in the size of my hand, where the platform is 5 centimeters, not 10 centimeters. So Simon, can you make me an antenna that can do that, to work at 400 megahertz? We'll see that we can get close to that, but the first thing that Tom was interested in was, and also when speaking with Costas, is let's get something that works at 1.1 gigahertz. So what we actually recently did was take that structure and make it actually electrically even smaller. So this structure here is suitable for that pico satellite platform. It's only 5 centimeters by 5 centimeters, and the total antenna height is less than 10 millimeters. So it's actually extremely compact. It's more compact than the previous one. This paper, or this idea, is actually currently being under review at a journal. So I'm an academic. This is what I do, is work with industry, work with colleagues to get ideas and to make things work practically, but also to publish papers and not get patents. So we made a prototype in the lab. Again, we didn't really have much significant budget to do it, not in the previous structure, but it still allowed proof of concept that things actually can still work for the structure. So the interesting additive feature of this is that the top plates were actually meandering. So this actually allowed the structures, the individual elements, to be electrically larger than they are mechanically. So this is the typical approach that we saw with the meandering of the feed circuit to actually get it to be fairly competitive. Okay, so here is the supporting feed system that's behind it. That was there, and we can see that we get fairly good agreement between measurements and simulations. So you can see, for example, the gain that we got of this very, very small antenna was roughly 3 dB measured in the lab. We simulated it to be 4.3, so considering that this is basically made out of aluminum foil by a student, it's actually pretty good. And it's decently matched as well at that frequency. And again, you can see a fairly good beam pattern, low cross polarization level, good axial ratio as before. Okay, so the next thought, we thought, well, let's see what else we can do. How can we even make this antenna more compact? So we thought, okay, well, if you use dielectric materials, going back to the PCB implementations earlier, you can actually use a very high dielectric constant material And what does that do? It makes your wavelengths smaller. So we thought, okay, the most important radiating element on this antenna is the very top length. So to reduce weight and everything, we thought, okay, how can we make this antenna, conform to weight constraints, but also be, having a smaller compact size, but also giving you that frequency that you desire. So this structure here is basically the best that we could do with achieving decent gain. So what we actually did is we introduced a PCB layer at the very, very top layer. So this made the wavelength actually smaller. So this, instead of doing meandering, which can be maybe a complicated design procedure, it simplifies the design because you just take a simple couple layers, put a PCB material in there, and that allows you to get a very, very compact antenna, more compact than the previous ones that we saw earlier, on the order of 0.2 lambda, or 0.12 lambda by 0.12 lambda. So again, what happens when you do this sort of miniaturization? You lose bandwidth. If that's okay, great, right? But you gain in terms of compact size. You also lose in terms of the total realized gain of the structure. So if we look at, say, the directivity, you're getting 3.6 dBIC. The realized gain was around 1, so 1.3. So that's pretty good for an antenna that's so compact. And again, that's with the feeding circuit and that sort of thing as well. And we made a prototype. So one thing that I think would be interesting to highlight is that Alba did their first Unicorn 2 antenna measurements in our lab. So this talk was really meant to sort of go over what we've done in terms of research, but also in collaboration with Alba and Costas as well. So I think when I started at Heriot-Watt about 4 years ago, Costas originally designed these antennas that are on the satellite now. I think I mentioned that. So it's very satisfying to see that these similar designs are actually in operation and working. And he came earlier to our lab to actually measure some of the first prototypes. So this is the Unicorn 2. I think you've seen it before, but the actual solar panels extend out. So this brings a little bit of complication, but I think we're just into the antenna world. But it also brings some novelty and some challenges, because one thing that Costa said was that we could try and integrate solar panels onto this satellite solar panel bus. So just to give you an idea, what Alba was up to with this original structure, they designed a 2.4 gigahertz circular polarized patch that would come out of their and be deployed. So this is going back to the more conventional approaches for antenna design, where you have a deployable system and also a UHF antenna. So this was all printed circuit board. Again, he's using a meandering concept to make it fairly small, which allows him to fit it onto the CubeSat platform. So they measured the UHF antenna in our lab, so roughly around 485 megahertz. So you can see the measurements, it's nicely matched. Pretty good agreement with simulations as well. So this was really nice to see, I think, for the Alba team. And you can see it kind of deployed there, the monopole antenna, when the camera shoots out, and you can see it actually visible there. And you can also see the next antenna we're sort of briefly talking about is a CP patch, which is there, and there it is in the anechoic chamber. Again, these were I think maybe the first or second proof of concept of these measurements in the anechoic chamber. And we had a really nice agreement between the measurements and simulations of this CP patch, again, because it's 2.4 gigahertz, it's a nice frequency, pretty good comparison between the reflection coefficient minimums and the measurements and simulations, which is always great to see. And again, fairly consistent beam patterns with measurements and simulations. Okay, so the other interesting thing that we've been doing recently, and this is actually supported by ESA, is to look at how we can integrate these types of antennas on solar panels. So if you look in the bottom left picture, the vision or the thought is anywhere you have a solar panel on a CubeSat or a picosatellite type of antenna, is can we put some sort of patch antenna? So this is not easy things to do, because as you've seen earlier, a patch is basically a microstrip piece of metal or a continuous flat top. So how do you actually allow light to go through? So we've looked at this a little bit, and we can actually make what are called mesh patches. So they consume maybe 90% of the original metal that's there. So you actually take away a lot of that existing metal that you would have in a conventional patch, and try and basically still allow the solar panel to work, but it's actually very tricky with Alba's platform because the solar panel is so thin. It's really hard to make these antennas work and actually radiate to some level of efficiency. So we've been looking at different strategies, different ways to do this. One thought is to have, as I think Costa showed earlier today, having an end fire antenna, so you can, on the edge there, radiate when that hatch goes up, and then you actually have a video camera there. You don't have communications for your 2.4 gigahertz antenna. So you need another antenna to get your downlink. So what we thought is having an end fire type of antenna, which could be another version of this, and I just don't have time to show it, but we've done it. But I'm going to show a little bit of detail of the structure here. So basically what you do is you have a PCB backing, you have your silicon layer, and then you have a glass layer on top, and on top of that layer you have your etched, very thin type of patch that's there. Okay? So given this structure here, we actually did some fairly decent measurements and simulations on our first prototype, and this is actually available on IEEE now. So we had a really good comparison between measurements and simulations. Again, the gain of this structure is almost approaching 5 dBi, or 5 dBiC, which actually is fairly high considering that you're on silicon. You know, the patch is meshed, right? So you're actually putting it and really changing the fundamentals of how the patch operates, yet it still works with a reasonable amount of circular polarized gain. So you can see here there's the gain, and the beam is quite a little bit tilted, but that's actually because there's, with this solar test panel that we actually had, there was biasing lines that introduced some anisotropy into the silicon layers that were there. So that actually twisted and tuned the beam pattern a little bit, because basically what happened is the propagation in one direction was slightly different from the other direction. So it wasn't a pure PCB material anymore. So you're probably all asking, well, how does this work from an optical point of view? Well, we did basic, simple measurements, put it in an anechoic chamber. Instead of having a reference antenna, we used a light. We used a light source. And you can see we basically had a transparent patch on top of the solar panel, had a light, measured the performance of the solar cell without the patch. So you can see here we actually measured and twisted the antenna versus beam angle. So with no antenna, with antenna, the voltage received was fairly consistent. So you're getting efficiencies of 90%, 80% over most of the radiated beam angle. And you can see that's the measurement experiment in the input chamber. Okay, so as a quick conclusion, introduce the concept of this voltage shorted patch, how we can integrate it, put it in an array configuration using CP, and how we need a feed system, sequential rotation, 90 degrees, right? And it's an evolution over the last couple of years working with Alba, with other PhD students and myself. We were able to get designs that are fairly compact, on the order of 0.12 lambda and 0.12 lambda, which is actually quite incredible, given that a typical patch is on the order of 0.5 lambda. So if I use some basic dimensions, right? If you're trying to do a UHF antenna, 400 megahertz, your wavelength is 750 millimeters, almost 3/4 of a meter. And if you're trying to put that on and have an antenna work, the typical way is to do deployables, right? Everyone has seen that today, but there's challenges, right? So how can we make a low-cost printed or antenna that doesn't deploy? Well, we can use this approach. It's just an alternative. But if you think about it, to put it on a 5 centimeter by 5 centimeter platform, right? So your wavelength is here, you're pulling it down to here. So just think of the challenges of that type of work, and it's actually very, very thrilling and challenging to get this to work. And I hope you appreciate the effort that goes involved with this antenna design efforts. Anyway, thanks very much. Is there any questions? Please. Yeah. We just measured the output voltage. That's the experiment that we did. Yeah, I mean, there's more things that you could do. This was a first prototype effort. But we're just looking for transparency, right? So what is the voltage when you have the patch there, and what is it when it's not? That's it. That's all we were trying to see. Yeah. Yeah, I did, we did do that. I did briefly go over it here. It's actually was published in this paper here. So it's a PCB version with vias. So the problem with this structure is it's heavy, right? Because it's a thick PCB material. So if you think about it, a typical, FR4 is maybe 0.6, 1 millimeter or so. Because this is like 10 millimeters, it's really thick. It's a stack. It looks like, in Star Trek, the cube. I call this the cube. It's a cube. Yeah. That was basically what that measurement that was done there. I can go to the end. Yeah, it was. We just took a solar panel that you could get at Radio Shack, and we put the mesh patch on top of it. So it was a conventional solar panel, like that you could get from Radio Shack. Yeah, there was the stack up illustrated on this slide. So you have ground plane, FR4 backing, silicon layer, okay, then a borosilicate glass layer, and then the mesh patch on top. So the thickness there in this implementation was around 3 millimeters, 3.5. So the efficiency of the antenna could be great, could be pretty good. But Costas and Tom are giving me really hard design work where the thickness of the glass and the PCB is on the order of 1 millimeter or less. So it's almost impossible to get a good patch to work in that constraints.
Yeah, we've been really mean on the requirements, to be honest.
But this is what drives innovation, right?
Yeah, it's like we really need it really thin, right? If you're really good and really thin, it's really tough. So,
Yeah.
Any more questions? Are we good? All right, we're good. Go.
Thanks very much, Craig.
So the final drinks, coffees, simplest, normal, and then just going to go to the training session after that. So about 15 minutes time, we'll be in the training session. So hydrate to refresh.
I know what to do. Is this my laptop or yours?
What?
Is this my laptop or yours? No.
Can use your laptop, that might be easier.
No.
Or this laptop,
No, I'm saying from Alba.
Oh, Haley's actually. Huh? A guy who works here like part time, like one day. I think he's left. I don't know. I think he's got a beard. If that helps. yeah. Okay. Let's move.